Welcome to School of PE podcast. I'm your host, Chris Miller, and I'm so glad that you could join me this week. We are going to discuss topics about FE, PE, and SC, and we're also going to answer questions that will help students prepare for their exams. Let's get started.
Hello, everyone, and welcome back to another exciting episode of the SOPE School of PE's podcast. I'm Chris Miller, and today I got a special guest with me, Mr. Sebastian Lobo-Guerrero. So let's welcome aboard. And Sebastian, if you could just kind of tell us a little bit about yourself.
All right, Chris, thank you very much, and thanks for the invitation for the show. Yes, so as you say, my name is Sebastian Lobo-Guerrero, and if you're wondering about the accent and all the letters, I'm originally from Bogota, Colombia. I was born and raised in South America. I came to the States about 21 years ago. I did my master's and PhD at the University of Pittsburgh, and since then I stay in Pittsburgh. And it's been a hell of a ride since then. I passed from the academic into consulting business about 17, 16 years ago. And basically, I work on a company that is called American Geotechnical and Environmental Services. We have three offices, one in Pittsburgh, one in Philly, and one in Virginia. And what we do is really geotechnical engineering for the transportation industry. That's our main market, working with DOT, PennDOT, Turnpike, different agencies. We also serve other industries, but transportation geotechnics is really what is our main market. Yeah, and then besides that, I'm extremely active in different professional societies like the Deep Foundation Institute and the American Society of Civil Engineers on the Geo-Institute, and pretty much anyone that wants to have me for a presentation or anything like that. I'm always very happy to share, our profession and try to motivate people to come in our industry.
All right, Sebastian, appreciate that background. Looks like my camera died, so I'm having some technical issues. So you might have to just stare at a black screen. So
That's all right.
it's like the Wizard of Oz, man, the man behind the curtain. So
Yes.
well, today we got an interesting topic. We're going to talk some geotechnical foundation engineering. So I think that's pretty exciting. We're going to talk about some shallow foundations, some deep foundations, and we'll see where we go from there. But let's start off by what in the heck are they, and what would they be used for? And let's start with shallow foundations.
Awesome. Yes, I think that's step number one. So, what is a foundation, right? I mean, I guess that's the main question. So, foundation is basically anything that connects some kind of superstructure into the ground, right? So, I
Mhm.
keep using the word superstructure or substructure, and for some listeners that are not made familiar with this, it's basically anything that you do. If it's a bridge, it will be an abutment or a pier. If it's a building, it's the building itself. So that has to be connected to the ground. And that is what is called the foundation, right? So we are all familiarized with solid foundations as a common term. So I'm trying to recreate what the human being did, I don't know, 6,000 years ago or even more. Um, I'm sure the first idea was, well, let's just put the structure on the ground, right? So they start just to construct things. Let's imagine pyramids. Let's imagine different houses, any kind of construction. You start putting on the ground, and then what happened? That if you put walls and things on the ground and you put too much weight compared to the bearing capacity, let's start introducing a few terms. Bearing capacity, or if you have too much settlement, you will notice that things sink in the ground, right? If I
Mhm.
put too much weight, they go down. Sometimes, and let's keep introducing terms, settlement is basically that deformation, that vertical deformation as it moves down when you put too much load. Bearing capacity will be actually a shear failure or some kind of failure that the structure goes through. But basically, when men and of course women start constructing these things, thousands of years ago, they noticed that they settle. So the first concept was to do what is called a spread footing. So a spread footing is just something that you put. Imagine a little bit of a block or something that you put the load, and it spreads the loads as it goes. Right. So that is a spread footing. You can see a spread footings on wall. You can see a spread footings for buildings. They will look like a block. Let's say 10 by 10 feet, 3 feet wide, 3 feet thick. And it's basically trying to get columns and things like that. Now, if your load is significantly higher and you cannot just do with the spread footings, then you go into what is called a slab. Many people are familiarized with, let's say, big warehouses. When you just
Mhm.
have a spread footing that is really big, in reality, for us, the design of a spread footing or a slab, it's similar in the respect of calculating bearing capacity and settlement, For a structural engineer, it's a little different because of the structural design. When you have a slab and it's a matte foundation that is very, let's say, very big, very wide compared to the thickness, they tend to use what is called the modulus of subgrade reaction, which is like little springs, and they can model the stresses inside the slab. But for geotechnical purposes, a slab and a spread footing are similar, it's just a different in size. So that is a step number one, and trying to recreate, right? So that trying to recreate the history of humankind, figuring out how to put load. So, all right. So you want to more questions about before we go into deep foundations, or you want me to keep rolling?
I got a question.
Hmm.
So you're talking the spread footings are basically the larger foundations, right? The more,
Correct.
like you were
Shallow
saying,
foundations, right?
correct.
Hmm.
So as they become bigger and bigger, does the strength of them get reduced?
Yes. So typically the bearing capacity, and this was studied by Terzaghi early on the last century. Bearing capacity is depending on the width. The width is always the smaller of the two dimensions of a footing. So let's say if I have a slab or a footing that is 10 by 20, the width will always be 10. It will be the smallest of the two. And bearing capacity is directly proportional to that. The bigger the width, the higher the bearing capacity. It also happens that the bigger the width, and the reason for this is because the bigger the width, the more the influence zone. So we talk in geotech engineering, we talk what is called an influence zones of about 2 times B, or 2 times the width. So if my footing is 10 feet, that
Hmm.
means my zone of influence in the ground, it's about 20 feet. And when
Mm,
I have a bigger zone of influence, I generate this shear failure surface that everyone that took like a soil mechanics or foundation class know what I'm talking about. Is this like the log, semi-log failure that goes like this. So the wider the footing, the biggest or the deeper the influence zone, the bigger the shear failures, the more resistance it can take. That is kind of like the basic principle.
I like it. That was well explained, so I appreciate that, Sebastian. So now we kind of have an idea about shallow foundations. So now let's go to the deep end or
All right.
deep foundations.
So then what happens? So humankind, men, women keep loading and doing bigger structures, and they realize that settlement continues happening and bearing capacity continue happening. So then somebody, I don't know how the process was, but I like to idealize it that somebody said, you know what? Screw this. Let's just make a hole in the ground and let's try to put some kind of post, some kind of pole, some kind of a foundation that
Hmm.
is deep, right? That it can go deeper. So that's where it comes the deep foundation. Now, deep foundations could be because of two reasons. One is that you have like, let's say that you have a weak strata or like a weak soil layer. So yeah, if I have a weak soil layer and I make a deep foundation, I'm bypassing that, right?
Hmm.
So I'm basically just taking the loads from here, putting it down here, and avoiding being in that middle layer. That is great if you have areas that have like shallow rock or something like that. But originally, being from Bogota, you don't have that luxury. In the middle of Bogota, it's a clay deposit that is hundreds of feet thick. So then what you do is that even though you are not bypassing the load, at least by having deep foundation elements, you can reduce settlement because they are going to work on friction, right?
Hmm.
They not only work on the end bearing, like if I load it here, not only on the end bearing, but as I have these elements, I have frictions on the side, what is called the shaft resistance. And that's the way that deep foundation started. So there are a couple different deep foundations because, let's say spread footings are a little easier. You have spreads or slabs, but when you go into deep foundations, it kind of goes into, let's say, into two big principles, which is displacement piles and
Hmm.
non-displacement piles. So going back into the concept, let me just get my pencil here. So the first concept is what? I have the ground and I'm going to put a deep foundation,
Hmm.
right? So the first thing, I just start hitting the heck out of it, right? I
Yeah.
just start driving it and driving it and driving it. Let me put it here. So as I drive it, as I push it, this goes into the ground and now works as a pile. That is probably the best pile in the sense of as I drive the pile, I displace volume, I displace
Uh-huh.
soils to the side, and I create what we call in geotech like a K value, which is just the earth pressure coefficient, which is how much resistance I get from the side. If anyone is familiar with active earth pressure or passive earth pressure, that's what it is. So as I drive this, I develop a really high lateral earth pressure coefficient. So that gives me a lot of friction because friction is a function of the normal force, as we all remember from physics.
Right.
So as I have more resistance on the side, I have more normal force, I have more shear going up. So that is the first deep foundation concept, right? So very good examples of that is what we were doing until, I don't know, 30 years ago. We were putting, wood posts,
Hmm.
right? I mean, taking a tree, cutting it, make a wood post, and just drive it. You can also do with H piles. That's another one. We also do precast concrete piles. Now, they are I mean, initially everything is fine. If you're in the middle of nowhere and you are driving one of these piles, we have these massive hammers with pile lids, and we generate a lot of noise and we generate a lot of vibrations. So as we evolve as a civilization, we don't have the luxury to come in the middle of a downtown and start banging the heck out of a pile, right? I mean, we can have noise, we can have vibrations, we can even liquefy soil. So then we start developing a whole portfolio or tools which is pre-drill piles, right? So then the concept of a drill shaft appears, and a drill shaft is basically just, instead of driving it, we just start drilling it, right? And as we
Mm.
drill down, now we don't generate that much noise, that we don't generate that much, energy, but then we are just taking the material out. Then we take the material out and then put some rebar and put some concrete, and now we got a caisson. Now, with those caissons, they have good resistance, but because the coefficient of lateral air pressure now is not the high value that we have when we drive, now we're allowing the let's say the walls of the shaft to relax, right? And when
Mm.
they relax, they have less normal force, less shear resistance going up. uh, but at the same time, now since we're doing a bigger element, we have end bearing, which is greater. So we start having drill shafts, for example, the Brooklyn Bridge, just for a
Hmm.
good example. That's a very old foundations, but we are kind of doing shafts, and we are going into, even though I don't know exactly if it's considered shaft because of the technology at that time. But anyway, we're going down and we're going more on end bearing. So the drill shaft not only has shaft capacity, but it also has end bearing. And then from there, we start having newer technologies, which is what it's very exciting on geotech engineering, because now we have, for example, micropiles, similar concept of pre-drilling stuff, right? And then taking it out, but it's smaller diameter, easy to construct, faster to construct. We also have permanent casing, which is what it helps us, yeah, keeping the walls. And it goes from there. I mean, the private industry continue to evolve and continue to
Hmm.
push new things. So we have what is called auger cast piles. So auger cast piles, for example, it's similar. It's just that it's an auger that is taken out. But there is also what is the drag the down, like the DD piles. There is the
Hmm.
CFA, which is continuous fly auger, and then DD piles, which actually push things to the side. So no, I'm not driving. I'm just putting a kind of like a tool in the middle, and as I go, I push. I don't drive, but I just push to the side. So it reduces vibrations and noise, but it still has the benefit of a higher K value. And then it goes from there. Some of these technologies are accepted already as common practice by transportation agencies like AASHTO and FHWA. Some are not. So, that's kind of when we go. Yeah, it also goes exciting into, for example, the helical piles, or we have some that are kind of like little screws that you put on the ground, and you, instead of driving or anything, you just kind of go in circles, and you put torque at the top, and that also gets axial resistance. So it's a very exciting technology with a lot of different variations. And it keeps going and going and going, and contractors end up finding new combinations of things that make it cost effective and exciting. So that's in a nutshell the world of deep foundations.
That's some great insight to both shallow and deep foundation. So, thanks,
Thanks.
Sebastian, for sharing that. So, whether it's engineering or shopping at the grocery store or watching TV on a Tuesday night, preferences play a big part in a lot of different things,
Hmm.
right? Some people might prefer, fish to chicken or something like that, right? But,
Yeah.
let's talk about preferences when it comes to foundations. So, is there a type of foundation that you prefer to work with?
Yes, yes, yes. But and before we go into that, there is some developments on the last, I don't know, I would say probably 20 years, maybe a little more, which is ground improvement. And that goes with this question because the world was divided into shallow foundations and deep foundations. But then many smart people coming from the contractor side came with the idea of saying, what if I do something that is constructed similar to deep foundations, but actually is not a structural element? It's just, let's say, let's make some holes on the ground, and let's put some, could be concrete columns, it could be ram aggregate piers, any, let's call it a stiffening element that we can put, right? And
Hmm.
then we put this, and what we do is two things. As we construct them, we densify the soil between the elements. And then at the top, we don't put any structural element, but we just put, some kind of load. And what we do is that now this soil becomes an equivalent mass. I mean, it's a composite mass. It has the effect of these stiffened elements, and it has the material inside that was the natural one. It does not work as a deep foundation because it's not rigidly connected. Any pile is going to be connected to a spread, to a cap, to a pile cap. This is not connected to anything. This is just on the ground, and you put a slab or a spread footing, but you improve the ground. So you construct it kind of as a deep foundation, but you analyze it as a spread footing or as a slab foundation. That is really fascinating, and there is plenty of companies around that have been doing really good business in the last 20 years with that. There is also different methods to install that, right? So you can have vibrated ones, for
Mm-hmm.
example, like Worcester does that in Florida. I was just visiting them a few weeks ago. You can also have ram aggregate piers like GeoPier and GeoStructures that they just kind of, you know, ram as they go. And there is like, the ones that they excavate. You also have concrete modulus columns by Menard, which is with a displacement tool, and then they inject grout under pressure. So it's fascinating, and it's all kind of technologies, and that gives us like a third option. So we have the world of shallow foundations, right? The
Mm-hmm.
world of deep foundations, and then right here in the middle, we have ground improvement. So that goes in the question of what is the process. So typically, as a good geotech, okay, so let's talk money because the technical aspect is great, but means nothing if we don't have the budget to do it. So typically, deep foundations are more expensive than shallow foundations. Uh, Very common sense understanding. If I just go and make a hole in the ground that is
Mm-hmm.
6 feet down and I pour concrete, well, that's cheaper than bringing a huge crane that has to dry piles and I have steel elements and things like that. So now it may not be always the case because it may be that you need a lot of excavation for a footing or a slab, and maybe you can get away with just a few number of piles. So I don't want to take my statement for every situation, but in general, spread footings or shallow foundations are cheaper
Mm-hmm.
than deep foundations, right? So the first step always is try to analyze if you can have a shallow foundation.
Hmm.
So you can get the loads. In my case, I'm a geotech engineer, so I get the loads from a structural engineer, right? And the structural engineer is going to tell me I'm going to need to put on that abutment, on that pier, or on that part of the building, or tank, or whatever they are doing. I'm going to need to put this much load. So I analyze it with a spread footing, and then I just make sure that it doesn't fail on bearing capacity and it doesn't have excessive deformation. So those are two very basic calcs that we all learn in soil mechanics and a class on foundation engineering. It's basically the main concerns that we have, right, on foundations. Can I take the load without failing the soil, right, without having this shear failure? Uh, and if I can, what is my allowable settlement? Our typical allowable settlement, it's about an inch, right? So it's basically I can have an inch of movement down. Soils deform elastic, soils deform consolidation. That's a whole different subject, but basically as geotech engineers we need to know how is the soil going to behave, how is it going to deform, can it take the load, and if it takes the load, how much is going to deflect. That's the first part. If that works, perfect, we move out, we finish the job, we move into another one, and that's it. If it doesn't, that's when we jump into either ground improvement
Mm-hmm.
or we jump into deep foundations. My personal approach is that I try the ground improvement first and see, can I improve the soil to take me to the level that I need? Can I reduce the deformation based on ground improvement? If I can do that and it works, perfect. I'm done. And if it can't, then I need to go to deep foundations, right? And then I typically start, can I drive piles? Like a good friend of mine, Mike Wasokit, he's the president of the Deep Foundation Institute, which I do a lot of work. It's a professional society that we do a lot of stuff. He always said the best found. I mean, his company, Thatcher Engineering, they work on installing piles. So obviously he's gonna try to sell driven piles, but he always say driven pile is a proven foundation, and it is because if I'm driving a pile and I'm going to bedrock, right, and we have different ways these days to confirm the capacity of piles, of driven piles, which is PDA, which is using the wave equation analysis. But without going too far, when you drive it, you have a way to know what is the capacity of that pile. So yes, if I do a driven pile, I do have a proof right there of that is working. Now that being said, you can also have different load tests on auger cast piles or micro piles or things like that. But everything I'm saying, every word that I'm saying after driven piles is becoming expensive and expensive and expensive. So, it's not only what technology can you do on deep foundations, but which one is better suited for your project and what will be more economical. And that's really that's really what makes my job cool too, because if you talk to different contractors, they're going to tell you their technologies are the best and they are the better suited. But as a consultant, I will never argue with a contractor that they know more about their technology than me, right? I mean, I'm not going to lie on that because they do day by day. But what I can tell you is that I know more of the whole portfolio, like of the whole catalog of options. And then I can decide which one is better, right? And then do a design on that one. So that is a very interesting interaction. And that's also what the Deep Foundation Institute is so great, because we basically all come together and exchange ideas and are kind of on the same page. So it's a cliche, but it's like we do really have a big toolbox with a lot of tools, right? So we just need to know what is the right one for the job.
That makes sense. Interesting, but yeah, actually, you're right. A lot of times, the dollar is what speaks the loudest, right? But
Not many times, always, man. Everything is money.
that's a true statement. No, that's interesting. Thanks for sharing that. So, anytime whether you're, you know, pounding something into the soil or
Hmm.
drilling into the soil or pouring something, you're gonna come across where you're gonna have to determine whether or not you're going to need an environmental assessment or you're going to need environmental permits will be needed. So how do you know, or at what point do you start thinking about those?
Yes, that's a really interesting question, because I mean, most of us, I'm saying like that we graduated 20 years ago or more. We didn't really have environmental classes, right? I mean, I
Hmm.
didn't have any environmental classes. So it's something that we kind of learn. I mean, I'm sure the new generations have, but I didn't. So I learned all these as I went through, right? The environmental aspect is extremely important because there are many contaminated soils. For me, for example, working in Southwest Pennsylvania, there is a lot of like byproduct of steel that have been buried in the ground for years. So when you get to a site, you need to know, first of all, you need to know, is there any environmental concern or not, right? And if they are, then how are you going to address it? So there is different ways that you can, mitigate that risk. You can do phase ones, phase two, phase threes, do investigation and see what you get. That also has a big impact on what we do, because, and we didn't mention it before we start pounding piles and putting spread footings and stuff, we need to do what is called test borings. And test borings is just making holes on the ground, trying to retrieve soil samples, trying to study properties as shear strength, classification, gradation, consolidation, right? We do consolidation tests. So even to do those test borings, you need to know if it's a contaminated site or not.
Hmm.
When we have investigations that we know are on contaminated sites, then we have what is called a HASP, health and safety plan for exploration. So we always need to go ahead and look on that. For that, we honestly rely on our environmental engineers, that they are the ones that kind of do a literature review. They look on everything that is available. We can do the exploration together if we take the proper precautions and we wear the things that are protecting us from the environmental contamination. We can take geotech samples, but we can also take environmental samples. So we test them together to see if what we have is it's safe or not. Uh, Different dangers that we have, byproducts of steel. You have, things from related to like oil and petroleum, right? So
Hmm.
we can be from diesel, gasoline. I have done a lot of projects that have heavy metals, which nobody wants to hear the word heavy metals, but they are, because they were basically buried in different lands use. And then asbestos, like natural occurring asbestos, could also be on rock. So we do a lot of that in Virginia. So there are different hazards that you should be aware before actually start even drilling. So it's extremely important to study that in detail and plan for that.
No, it makes a lot of sense. So now, we kind of talked about whether you needed like an environmental assessment or environmental permits, but what happens? I mean, you're dealing with soil or
Mhm.
foundations. So what happens if the project that you happen to be working on is in a flood hazard zone?
Yes, that's another great area, which is if you have, and that happens a lot here in Pittsburgh because we have the three rivers next to us. The main effect that you have on that, there are two things, but the main one is scour. So when you have some kind of flood around, it can scour. And FHWA did a study, I don't know, probably it's now 15 years old, and they determined that, I don't remember the exact number. I could maybe making it up, but it's something like 90% of bridge failures related to foundations are due to scour. It's basically you have all these piles or you have these spread footings, and you literally just take the support tower out. So you scour the support tower for the substructure, and things end up failing. So scour is a big deal. We design for scour. There is all kind of rules that we have to follow in terms of where we place the bottom of the pile cap, where we place the bottom of the footing, and things like that. Now, the other part is when you have like a water level that goes up and down, you also have to analyze corrosion, potential of corrosion, things like that, right? If you did steel pipes that I was selling before, right? If you have a steel section that is, that is in constant contact with water or with soil that has potential for corrosion, that could also be a factor. So all that, and all that is truly today, when you take the design manuals that we have, all that is accounted for.
That makes sense. Now, something just kind of popped into my head as you mentioned bridges. When I usually think of bridges or buildings, I usually think of a structural engineer, right?
Yes.
So, they're going and they're testing maybe the bearing capacity or the structural to make sure there's no damage or anything like that. But now that I'm, talking to you and you talking about soil and foundation, I started thinking, what about the foundations for bridges and buildings? How often do
Mhm.
these need to be examined or evaluated?
Yes. Well, unfortunately, part of that is that you cannot see them, right? I always say you will never see my best work because it's all buried. You will never see my best work because it's buried on the ground, so you cannot really see it. So it's hard to really see those foundations. It's hard to inspect them. However, you can get an idea of what is going on based on the behavior on top, right? So if you see settlement, right, on the building, well, that is related to a foundation issue. You may not be seeing the pile, but you can monitor it as it moves down. So more than the inspecting the foundation itself, you can see if the foundation is working or not. And then that kind of take us into another field on our profession, which is retrofit,
Hmm.
right? So we do a lot of retrofits too. When you have things that are settling or something, we can use, for example, micropiles. It's a very common tool that we have to go and drill additional like mini piles that can now take the load. If you have piles that are probably corroding, we can also go and do different things. So there are different tools and different options to deal with that, but mostly, you know, it's not really examining the foundation itself, is the effects of the foundation. Now, that being said, we have a lot of tools to examine the foundation while it's being constructed. And probably drill shafts is the best example. We have awesome companies like Pile Dynamics and GRL that have developed all kind of monitoring tools. So when we construct the drill shaft, we know the integrity of the concrete. And we have all kind of fancy toys that we can look inside the shafts with little cameras and temperature sensors, and we send ultrasonic pulse waves from one side to the other on the shaft, and we see if the concrete has good quality. And that is really exciting because all that has come in the last, I don't know, 20 years maybe.
Hmm.
So I have been part of all that change, and it's awesome to see how things evolve, right? And be on top of that. It's I always say geotechnical engineering is something that has been around forever. I mean, I'm not claiming to be one of the first engineers to put a put a stick on the ground and say that's a foundation. That has been done forever. But I think what I say that we are the first one is to completely understand. I mean, before they knew that it worked because they put it and it didn't settle, right? But now we can predict it and we can anticipate that,
Hmm.
and that is all the exciting part. I mean, when you think about foundation engineering, the way that Terzaghi started, we are less than 100 years old, right? I mean, I have the luxury to say that I met Peck, Ralph Peck, which is the father of foundations,
Oh, wow.
and I can say that I listened to his presentations toward the very early part of my career and the late part of his life, but I still have that opportunity. So then you see that it's something that even though humankind has been doing it forever, it's kind of new. It's kind of like a
Hmm.
new thing.
That's pretty cool. It's funny is, I do these podcasts, I talk to, transportation engineers,
Hmm.
structural water. I mean, and it's interesting to hear about what you guys do because everyone does something a little bit different. So let me throw this scenario out there for you, Sebastian. I just
Hmm.
was thinking about it as you were talking about this last point. So let's say we're up in Northern California and
Hmm.
an earthquake had hit. And you always hear about after an earthquake, you want to go and inspect the structural of a building or even a bridge. What are you doing from the geotech side?
Yeah, so again, we're kind of dealing with the consequences at that point, making sure that things didn't fail. For the I mean, seismic is a huge part in geotech, right? So we need to predict. The obvious thing that comes is the loading. During a
Hmm.
seismic event, you are going to have more load, right, because of inertial forces. So we need to we need to plan for that. But probably the biggest part and what has been the biggest development on geotech on the seismic aspect is potential for liquefaction. And basically liquefaction is when you have a sand that is saturated. So imagine that you have a loose sand. So it's like
Hmm.
a bunch of spheres, right? And it's completely saturated. When you have an earthquake, you get a shear force that come and, it's a lateral force or could be a little vertical too. But basically try to push these spheres together and they generate what is called the excess water pressure. Uh, Let me just put an example. Imagine that you have a lot of spheres inside a balloon, and when you move it, they try to they try to kind of compress, right?
Hmm.
Like the spheres are going to try to compress. The water is it's taking the pressure, and when the water takes the pressure, sometimes he doesn't like it and just fluid, like it basically just has so much pressure that it just separates the particles and liquefied. It's the same thing as running sands. You can also do it by doing an excavation too quick with sand and a high water table, that you basically just generate the water to push everything up.
Wow.
So every time that you do things like that, you liquefy the soil and it becomes, like the movies that when we were growing up, like the running sands in the desert
Yeah.
that people just sink, that exactly happens. And there is plenty of liquefaction evidence around the world on different earthquakes. You have sand boils, you have all kind of things. But the worst thing for foundation is that they basically are now supported on a SOPE. And when you are supported on a SOPE, things sink immediately. Most of the earthquakes that you see on the consequence related to geotech is liquefaction effects. Uh, the beautiful part on all that is that thanks to the work of Sid and Idris, they basically develop all these methods that we can. And it was part from Berkeley in California and also on MIT. We developed methods that we can predict the susceptibility for liquefaction, and that was the first step in the, I believe, late 60s, 70s. Then that school continued. We have great minds like Jonathan Bray and Ellen Rache, and I mean it's plenty of great knowledge in that area that we can use. And the other awesome part is that then contractors end up coming with ways that we can mitigate that liquefaction. So we can install sand drains, we can do ground improvement. There is a lot of work that has been done by Kenny Stockhausen, University of Texas in Austin, of different ways that we can mitigate liquefaction potential. So, and it's very interesting because liquefaction and I guess seismic for me it's great because I grew up in Colombia where everything is designed by seismic in mind because that's probably the biggest demand that you have. But then I moved into this part of the country in the US and I have spent the last 21 years of my life when we don't have seismic, right?
Hmm.
So I didn't really do much seismic engineering for a while. But then I start having projects in South America and I start dealing with the seismic aspect again. So, kind of have to, I mean, I don't think that I ever forgot the concepts, but definitely had to start brushing up on my codes and things like that. So, yeah, seismic definitely is I would say it's probably the newest part on geotech engineering. And again, it's not that seismic hasn't occurred before. It's just that now we have tools to understand
Hmm.
and address those concerns that we didn't have before. I mean, I think before it's, because when I said all this, I'm sure somebody's listening and said, this guy is full of smoke because, we have been doing bridges and we have been doing this for 200 years ago. If you look, I have a few books here that are very classic, like the first edition of really old foundations book before Terzaghi, before Peck. And basically what they were tables. They were just
Hmm.
tables telling you what is a good pressure that you can put. So I mean, it goes as fundamental as saying if you have a sand that is medium dense, you can put 2 TSF as a bearing pressure, right? No calcs, no investigation, nothing. And yes, they did that, right? They did that 200 years ago, 150 years ago, but they also had a lot of failures, right? It's
Right.
just that we only see the buildings that stand. So it's just that understanding what is really the new part, right? It is the understanding and the ability to design on a safe way instead of just winging it, putting something and dealing with the consequences. That's basically the change.
No, that makes sense. I appreciate that. As we're running to the end of this episode for today, I know we've kind of got sidetracked. I got one last question that probably has
Yes.
absolutely nothing to do with what we were scheduled to talk about, but now I'm curious.
Man, we didn't cover anything that we are gonna need episode 2, episode 3
Oh,
and keep
at
going.
least. I never thought I'd hear myself say, "Hey, I could talk geotech all day."
Oh,
This
we
is
can. And you give me alcohol and I can talk all night.
but let me ask you this, Sebastian, and I'll let you go for the day. You talk about this whole liquefaction of soil,
Mhm.
and now my mind is thinking, what about quicksand? Is that what it is?
That is exactly what it is, quicksand. So quicksand, running sand, liquefaction, it just depends of how fancy you want to express it. But it's always the same phenomenon, which is a loose sand that is saturated and you put a shear force. And as a result, I mean, remember, imagine that I have a sphere on top of a sphere.
Right.
They have a big volume. The moment that they roll and they try to compress, that's when liquefaction happens. A very simple way to visualize it is if you have a sphere on a 2D plane, Yeah, I have a sphere here, one up, one down, one side, one the other side. That's a four contact, right? The
Hmm.
moment that I roll it over, it goes into kind of like the voids between the adjacent two, and it goes into a 6 point contact. That is what is called like, an hexagonal package. That one reduces the volume of voids in between. So if it's saturated, the moment that I do that, I generate excess pore water pressure. And as I say, the water just said, I'm not gonna take it, and just push everything around, just push everything away, and then your soil completely has no strength because it's basically just grains of sand floating. And I know it sounds very dramatic and it's hard to imagine that happen, but it does. When you look pictures from different earthquakes, like Kobe in Japan 1995, or
Right.
Christchurch, you see these gigantic sand balls coming out. It made sometimes the sand balls go all the way to the surface, sometimes they don't, and then things just think. But yeah, it is everywhere, and as I said, you can even generate it not even without seismic. Just if you have a high water table and you have a lot of sand and you make an excavation, you create what is called a hydraulic gradient, because you have water up
Hmm.
here, water down here, and water is going to flow from high to low energy, and that flow end up having quicksands, or any kind of fluidization of sand. That's pretty much what it is.
I appreciate that insight. I'm going to leave a cliffhanger because we got to get you back anyway, Sebastian. Because I
Sure,
didn't get it.
absolutely.
I didn't get us anywhere.
I'm
Well,
always happy to come back, man.
so we're going to leave on a cliffhanger, and I'll leave this out a question, and you don't have to answer the question. We can answer it next time.
Hmm.
So when I talk to like architectural engineers, they
Hmm.
talk about how the differences in technique or styles varies from uh, north of the northeast to the southwest to the Pacific Northwest.
Hmm.
So with geotech, does the approach and techniques also vary if you were doing something in, say, the Southwest in New Mexico versus the flatlands in the Midwest in Ohio? Don't have to answer it. We'll leave it for next time. But Sebastian, hey, I appreciate you coming out here today talking some geotech, and love to have you back. So for everyone out there, have a great rest of the week. Sebastian, thanks for coming on, and we'll get you back on here for another episode.
Absolutely. Thank you very much, Chris, for the invitation. I know I talk too much, but hey, that's the price that comes with me. But the positives, I'm always willing to come back, and explain more and more and more.
I appreciate that. So again, everyone have a great rest of the week and enjoy the summer.
All right. Awesome. Bye.